It's time for chapter 7. We discussed in chapter 6 substitution and elimination reactions. Okay, that's what chapter 6 was. Chapter 7 is like a continuation of chapter 6. So let's dig in. We will cover 3 functional groups, generally alcohols, phenols, where you have the aromatic ring with OH, and thiols. Of course, those ones will have SHs. Okay, alternatively it could be in this form. So now let's dig in. I see an OH here. I see OH, I see OH, I see OH, OH, OH. So majorly we'll talk about alcohols in chapter 7. How do we name them? How do we name alcohols? One carbon will be methanol, so it should have been methane as in alkanes, but now we replace the E part with OL. So 2 carbons, ethanol. Remember, when the hydrogen is gone, you get O minus, that one will be ethoxide. The salt, if the hydrogen is gone, you get CH3O, that one is methoxide. Okay, so anyway, alcohol is on the first carbon here. We now say 1 propanol. Notice that here we did not say 1 methanol, 1 ethanol, because it has no choice. Whether it's on the left or on the right, it's always on the first carbon. But here, the OH can be in the middle, right? Like what you have here. Now the OH is on the second carbon, so 2 propanol. This is what we call isopropanol, what you guys use in cleaning your wounds. Other is called rubbing alcohol. It's mostly isopropyl alcohol. And then here you have 4 carbons, so it's 1 butanol. The OH can be anywhere. For example, here it's on the second carbon, so it's 2 butanol. Other is called sec-butyl alcohol. The N here is just means normal, like the regular. That's the regular butanol or normal butanol. Sec because it's on the second carbon. And then this one is isobutyl alcohol, because of course you will have 4 carbons with some sort of symmetry in there, so it's isobutyl alcohol. But in nomenclature you prioritize the position of the OH, so it's 1, 2, 3. So it's 1 propanol, and then the methyl becomes a substituent. It's on the second carbon. Here prioritize the position of the alcohol and then look for the longest chain. So we'll go 1, 2, 3. That's the longest chain, not 1, 2, because that will be a shorter chain. Okay, not like that. So you go either up or down. You get 2 propanol, there are 3 carbons. This becomes a substituent, it's on the second carbon. Other is called tert-butyl alcohol. We use it as a solvent in E2 whenever you use the bulky base. What if when you have a double bond? Would you prioritize the OH or the alkene? Turns out the OH is prioritized over the pi bond. Okay, so now it's still propanol, but it's supposed to be propene because it's an alkene. Replace the E with OL, you get propanol, but the alcohol is on the first carbon, so it's propene 1-ol. Other is called allyl alcohol because this part here is allylic system. Okay, that structure is allylic, where you have a double bond, a single bond to a carbon, and then to something else like OH. This part here is called an allyl group. When it's a ring and it's only OH is the only substituent, you just say cyclohexanol or cyclohexyl alcohol, where the cyclohexyl will be a substituent. Now here this is not phenol. This is called the benzyl group. Like from here to this CH2, that part is called a benzyl. Otherwise, you gonna consider it to be a methanol. You see how methanol has 3 OHs, right? But I can stretch out one hydrogen, and then now I replace this hydrogen with the ring, with the benzene ring. You see how I built into the structure? So the name can be derived from methanol because this part right here is like methanol without one hydrogen on the C. So and then this part right here, it's a phenol. That's a phenol. We talked about that, I think, in chapter 4. That's a phenol. So you can call it phenylmethanol with UPAC name. The common name would be benzyl alcohol. This is UPAC, that's common. Okay, so what are the types of alcohols? The reference alcohol is gonna be methanol. Again, I would want to write methanol like this. Why? Because we want to replace the first hydrogen with a carbon structure, then it becomes a primary alcohol. Example of a primary alcohol is ethanol. That's the babiest primary alcohol. Otherwise, it can be propanol, it can be 1-propanol, it can be butanol, hexanol, decanol, all that. All those are primaries. And then secondary alcohols, okay, now from methanol, we are going to replace 2 hydrogens. So 2 hydrogens are replaced by a carbon containing group. You replace these 2 with R groups. Then it becomes secondary because there are 2 R groups, 2 carbon containing groups. The babiest example I can show you is rubbing alcohol, isopropanol, right? Isopropanol is a secondary alcohol because there are 2 alkyl groups. Tertiary alcohol. Now all the hydrogens are replaced. All the hydrogens on methanol or reference are replaced. You replace all these guys with R groups. The best example, smallest example for this is tert-butanol. You have 3 alkyl groups and an OH. That's just an example. Otherwise, it can be so many things. That's tertiary. It can be a ring with OH, metal in the ring. This is still tertiary. It could be so many things. You could have 3 benzyl groups, phenol groups. See, this is triphenyl alcohol. So long as you have 3 R groups, you have a tertiary alcohol, okay? All right, so when the ring is aromatic and it's a benzene and you have OH on it, directly on it, that's called a phenol. This is not a phenol. This is the most confused structure. Students usually call this a phenol. No, we say this is benzyl alcohol. OH gets priority, so 1, 2, 3, 4. This can be called 4-chlorophenol. Otherwise, it can be called para-chlorophenol because the chloro is on the 4th carbon. Here you have the bromines on the orthos and the para, so it's hard to say ortho, para, tribromo. No, that sounds messy. So we use the numbering system. So it will be 2, 4, 6. There are 3 bromines, 2 tribromophenol. Okay. Sometimes the OH can be sitting on a ring with other carbonyl containing compounds like aldehydes. So I'm just trying to show you the carbonyls as I get rid of the stuff. So this one, it's an alcohol. Okay. Oh, this one is an aldehyde with an alcohol on the 4th position. So the aldehyde takes priority. So it's called benzaldehyde. but the OH is on the para position, fourth position. Okay, here the OH is on the meta position to your reference group, which is a carboxylic acid. So that tells you when you have aldehydes and carboxylic acids, they take priority. So now OH becomes a substituent. So instead of all, we are using the name hydroxyl. So meta hydroxy benzoic acid. Okay, this one is a phenol. We know that it's like this guy here. The nitro does not replace the phenol in the parent name, so the nitro is on the fourth position of the OH, so it's para-nitrophenol, not para-hydroxynitrobenzene. No. Okay. Hydrogen bonding. You've heard of hydrogen bonding so many times. Hydrogen bonding is simply the attraction of one molecule to another. This is an intermolecular force of attraction. I think we discussed about this before, so you see it here again. This usually happens between molecules which have hydrogens bonded onto oxygen, nitrogen, and I think also fluorine. Okay, such molecules will do hydrogen bonding between themselves. That's why it's inter means between molecules. So the best example is water. We say dipole moments point towards the electronegative element. Oxygen is partially negative, hydrogen partially positive. Bring a second molecule of water. The partially negative oxygen will be attracted to the partially positive hydrogen of the second molecule. The forces between the two is what we call hydrogen bonding. So if water does it, then one would expect a molecule like ethanol to do it, right? If you bring two ethanols, you're gonna get hydrogen bonding between the partially negative oxygen and the partially positive hydrogen of the second molecule of ethanol. So you see, those are intermolecular forces. Now let's look at the alcohols and their solubilities in water. Okay, so the principle for those taking the lab, the principle like dissolves like is very important in organic chemistry. So if something is polar, it's gonna dissolve in polar solvents. So polar solids dissolves in polar solvents. Let's look at the boiling points and let's look at the scale, the solubility scale. So we are looking at how many grams of these alcohols can dissolve in 100 grams of water. Okay, so methanol, there's no way you can measure how many grams dissolve in water. You cannot measure how many grams of methanol can dissolve in water. Why? They readily dissolve. The molecules readily dissolve. So if you take a methanol molecule and then bring it close to water molecule, they are resembling, right? And they are like almost same size. So the solubility is infinite. You get hydrogen bonding. It's the hydrogen bonding that helps the solubility to happen. So let me write it here where you can see. So you get hydrogen bonding between the methanol and the water. Because the oxygen is partially negative, the hydrogen of methanol is partially positive. Okay, so like I said, you get H bonding in between them. All right, so methanol infinitely dissolves in water. Ethanol is still small, infinitely dissolves in water. Propanol still small, but when you get to 4 carbons of an alcohol, now solubility decreases. Butanol has a solubility of 7.9 grams per 100 grams of water. Why is it so? The reason is, in butanol you have extra covalent bonds which are now creating a tail, a hydrophobic tail, right? Water-hating tail. So the molecule will not want to dissolve. So this side is polar in butanol. This is the structure of butanol. It should be CH3, CH2, 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 OH. This side here, where you have the carbons and hydrogens only, that side is hydrophobic. Okay, so now you have much of the hydrophobic water-hating part on the molecule than the water-loving hydrophilic part. Then the solubility decreases. Of course, pentanol has even more carbons, so solubility will decrease. 2.7 grams of pentanol per 100 grams of water. Hexanol has 6 carbons, you see. Now the solubility even too low, 0.6 grams of hexanol in 100 grams of water. So the summary is, the more covalent bonds, the more CH covalent bonds and CC covalent bonds you have, the less soluble this molecule will be in water. So methanol, ethanol, propanol infinitely dissolves. But more than 3 carbons, solubility decreases because you are increasing the number of covalent bonds which are stronger than hydrogen bonds. Covalent bonds are always stronger than hydrogen bonds. Okay. Acidity of alcohols and phenols. Phenols are alcohols, but they are aromatic alcohols. They are special alcohols. So alcohols are weak acids and they are very similar to water. The structure of water is like this, HOH. The structure of alcohol will have a carbon containing group and OH. So they are very similar. The smallest alcohol obviously is methanol. And then the one we drink in beer is mostly ethanol. Now, whatever water does, the alcohol will tend to do. So now, if you introduce a base, okay, let's say we have a base strong enough to steal this hydrogen, what happens to the bond in between? Those 2 electrons are taken to the oxygen next door because oxygens are electronegative. Oxygens are electronegative. So the base will pick up the hydrogen. This bond goes on there. Okay. So which means it is possible for OH to lose its hydrogen to give you the alkoxide, like methoxide, ethoxide, propoxide, butoxide, pentoxide, hexoxide, and all those. So the hydrogen is lost. This is lost to base. The pKa, which is the ability of the acid to ionize for alcohols, is roughly between 16 to 15. The pKa of water is somewhere 15.7. So you see they are very close. Now, if the alcohol is aromatic, so let's say you have a phenol. What happens if the base takes out the hydrogen, the acidic hydrogen? You get what we call a phenoxide. And the phenoxide can do resonances. You push it, goes there. You push this one here, the 2 electrons come here, they're here, you get a negative charge. Looks like a sad face. Then you push the lone pair here, the lone pair comes here. When these pi bonds open up, you get that. So bottom line is, the conjugate base formed, because these are conjugate bases, the conjugate bases are resonance stabilized. And that's why phenols resonance stabilized. That's why phenols are more acidic than regular alcohols. So like if you have a regular alcohol, for example a CH3OH, this one will be a weak acid than this, because once the CH3OH loses the hydrogen, all you have is an O-, and there's no way to do resonances because there's no pi bond next door. Here, once you lose the hydrogen, you can use the pi bond to do resonances. So phenols are more acidic than regular alcohols because the conjugate base, the anion formed, which is the conjugate base, is resonance stabilized. Here there's no resonance, okay? No resonance stabilization. So the electrons cannot be delocalized or stabilized. So in fact, this guy is a strong base. The alkoxide formed here is a strong base because there's no resonances. These conjugate anions, these guys are weak bases because they are resonance stabilized. Okay. The acidity of regular alcohols, let's say an alcohol like ethanol, its acidity can be increased by introducing electron drawing groups. So if you have hydrogens here, replace those hydrogens with fluorines. Okay. That way, if this molecule loses a hydrogen, you have this structure. So the electrons are pulled in to the structure by inductive effect because the fluorines are electronegative. Here, there's no inductive effect as much. If this guy loses the acidic hydrogen, you get O negative. Okay. So here, no inductive stabilization. Remember, it's not resonance. We are talking about inductive effect, which is electron pull through bond. Here, this one is stabilized by inductive effect. Remember, inductive effect is just electron pull through bond or electron donation through bond. In this case, it's electron pull through bond because these fluorines are highly electronegative. So electron withdrawing groups at the alpha carbon, which is just a carbon next door to the alcohol, will stabilize the conjugate anion. So the anion here is stabilized, and if it's stabilized, you get a weaker base. If it's a weaker base, it must have come from a stronger acid. So you see the pKa of this molecule with 3 fluorines is 12.4. The pKa of ethanol with just hydrogens is 16. So this structure right here is more acidic than this because we said the lower the pKa, the higher the acidity. We said that, I don't know if it was chapter 1 or 2. So this one is more acidic, and it's evidenced by the electron drawing groups which are stabilizing the base, the anion. The weaker the conjugate base formed after losing the hydrogen, the stronger the parent acid, which is this guy. Same can be attributed to phenols. So a regular phenol has 5 hydrogens on it. The moment you introduce an electron drawing group, like a nitro group, that's an electron drawing group because the nitrogen has a plus sign on it. We talked about this in chapter 4, right? So if you have electron drawing group, that helps because once the acidic hydrogen is taken out, once a base is used to take out this hydrogen, You put the 2 electrons that made the bond between O and H, give it to the oxygen, you get O minus. Now, the O minus can use its lone pair to do resonances. So the resonances is what is shown here. Okay, but both the phenol and the paranitrobenzene can do resonances. The question is, who has a greater pull of these lone pairs into the ring? Because nitrogen pulls electrons towards itself because it's highly electronegative, it's highly an electron drawing group, then you get more stabilization. And in fact, where you have 3 nitro groups, there is even much greater stabilization. That's why picric acid will be the stronger acid of the 3. So you're looking at picric acid, which has 3 nitros. So the more the electron drawing group, the more acidic the molecule. That's the bottom line we are saying here. The more the electron donating groups you have, the less acidic it's gonna be. So the phenol here is paranitrophenol, so the nitro, only one nitro on para, and then you have your reference phenol ring. Okay, so the phenol ring is 10, has a pKa of 10. It's obviously more acidic than, say, ethanol, which has a pH of 16, or any other regular alcohols which have pH of 16. You're introducing an electron drawing group, only one, pH drops, which means it becomes more acidic or likely to lose this acidic hydrogen. That's what more acidic means. You introduce 2 more nitro groups, like in picric acid, pH drops to 0.25. That's like it's almost as acidic as a regular HCl, all because of the electron drawing groups. Okay. Acidity of alcohols and phenols. Once you treat an alcohol with sodium, and this would have done if we were doing phase instruction, I would have brought metallic sodium and say ethanol in a flask and then drop it in there. The sodium will violently react and dart on the surface of the liquid, and there would have been a lot of gas formed, which is hydrogen gas. So that's what's shown here. So the sodium ionizes as it takes out the hydrogen of the alcohol, and the oxygen takes the negative charge because those 2 electrons will be donated to the oxygen. That's generally what's happening here. Okay, so to be clear again, when you add sodium or potassium to an alcohol, just like it will do in water, you're gonna lose hydrogen gas, half of it, because only 1 hydrogen is lost. Okay, and then the 2 electrons that made the bond between O and H are given and donated to oxygen because oxygen is more electronegative. So you have 3 lone pairs because here we do have 2 lone pairs. Sodium itself ionizes, and then you get the alcohol version, the alkoxide version of the alcohol. Now, what if you treat with sodium hydride or potassium hydride? Again, this guy is an ionic compound, so all you have is Na plus and H minus. So you'll use this as a base, use the hydride portion as a base to steal the hydrogen, and then these 2 electrons again are donated towards the oxygen. You get 3 lone pairs. You started with 2 lone pairs. As this hydrogen takes that hydrogen off, you get hydrogen gas. Okay, so which means alcohols can behave as acids because by definitions acids are proton donors. You see how this alcohol is losing a proton to form hydrogen gas. Even this one is losing a proton to the base. So these alcohols are playing the role of acids because they are donating a proton. If you take, I'm gonna draw the ring again for clarity. If you take phenol and react it with sodium hydroxide, again, this is ionic, so I would rather write it like that. So the hydroxide part of sodium hydroxide will come and take off this hydrogen, because now we know that phenols are acidic, they are proton donors. So what do you get? You get the conjugate base, we call it phenoxide, and the sodium part becomes a spectator ion, and the OH minus that accepted the hydrogen forms H2O, which is what you have here. So this came from phenol, so we call it a phenoxide. It's a special type of an alkoxide. Sodium hydroxide played the role of a base, the phenol played the role of an acid. Okay. Now phenoxide can later be used for other reactions. Now, can alcohol play the role of a base, which means can they accept a proton? Regular alcohols will accept, phenol will not. Let's explain why. So you can use a lone pair of the OH of the alcohol to accept a proton. So in that case, this is a base, and of course this is an acid. So because you used one lone pair, the oxygen will get a valency of +1. Alternatively, use your formal charge calculation, which is just the valent electrons minus non-bonding electrons minus number of bonds. So in this case, this oxygen right here has a valency of 6 on the periodic table. Non-bonding electrons, there are 2, and then bonding electrons, there are 3. 6 minus 5 is +1. That's where this positive came from. So this is just showing you how the alcohol can be protonated, and then in turn the OH becomes a good leaving group, because now this can fall off and you're gonna make a carbocation on sp3 carbon. Remember, this is carbocation on sp. That used to be sp3 carbon, so now it's sp2. This is sp3, right? Once you lose the water, you've lost one electron domain, it becomes sp2. And that's what we said carbocations make. They make positively charged carbon centers, which are sp2 hybridized. Okay, so this structure right here is called alkyloxonium ion, which usually breed or make good leaving groups, a good leaving group out of OH, which will fall off as water. Okay, so when the water falls off, you get a carbocation and H2O. All right. What of phenols? Phenols will not do it, because the water will not want to fall to make a carbocation. If you try to make a carbocation, this center here only has 2 electron domains, is sp hybridized. Last time I checked, the molecular geometry of sp hybridized center is linear. Do you see this to be linear? No. That's why phenols don't easily accept protons, just like the regular alcohols like ethanol would do. Okay, because now that would have made it to be linear. Okay, that will force the carbocation to be linear. Obviously it's not, therefore it will not do it. And that's for the same reason, that's why phenols do not do SN1, because SN1 will lead to formation of such a carbocation, which is not linear evidently, and SN2 will not happen again, because this carbon right here is carrying a group that's a bad leaving group. That one is one of the worst leaving groups, because if it leaves, it's gonna make OH minus, which is a strong base, And what did we say about leaving group? Leaving groups must form weak bases after they leave. So OH of phenol does not do SN2 or SN1. We will continue from here with dehydration of alcohols next time.